Okay, hello everybody, welcome back. We are on part 2 of CNNs, and so let's go.
Okay, hi everyone, and welcome back. So remember last week we covered some basics of CNNs, namely that it contains a filter. A filter is like this dark blue square here, or I mean it could be a rectangle as well, or basically any shape filter that has a fixed weight. Over here the weights are 0, 1, 2, 2, 2, 0, 0, 1, 2. And so then we move the filter along the image. It's like looking at a very restricted scope, and then you go through the like you look through at different parts based on your different parameters. So just to recap, we have this thing called the padding. Okay, the padding is the boundary of zeros. Okay, usually it's zeros. Okay, and then the stripe is basically how many like squares to move the filter by or the kernel by each time step. Okay, so all good with that? Okay, so today what I'll do is I'll cover the remainder of the theory behind CNNs, and then later we'll look at a practical example using the Jupyter Notebook. All right, so I hope you are ready. Okay, because today's topic is the theory behind it will be a little more intense. Okay, but it should be a build up of what we have already learned from this. Okay, so we move on to the next part. So the next part is called type of paddings. So the type of paddings that TensorFlow uses, I think PyTorch uses the same thing as well. There are two main types. Okay, one type is called the same padding, and the other type is called the valid padding. So in same padding, what happens is that we will zero pad the boundary, as you can see over here. This is the zero padding here. So we will zero pad the boundary, okay, and then we will use the the respective stripe. Okay, in this case, this is stripe 1. Okay, so that once we apply the same stripes, okay, you see our input image is a 5 by 5. Okay, input dimensions is 5 by 5, and our output dimensions is also a 5 by 5. Okay, because of the padding that we use. So the padding is padding 1. So padding equals to 1 over here. So you can see that if you use a 3 by 3 filter and then you do a padding of 1 on each side, you will get back also a 5 by 5. Okay, if we use the valid padding instead of the same padding, what will happen is as we look through this filter, okay, this filter will go 3 times. One time here, so this corresponds to this. Okay, not 3. Over here, this is a stripe of 2 in this diagram. So the second filter will be this one, and then it will link to this. Yeah, of course, if you look at the other two, I mean, for completeness, let me just draw. So the other two will be the filter at this part here, and then this will be this square. And then the last one will be like the filter at this bottom right. So you can see that if we like use a valid padding and we like keep the stripes to be, like over here the stripe is 2. You can see that what will happen is that we will get a narrowing of the output dimensions. So over here, the output dimension is 2 by 2. Yeah. So based on the type of padding you use, okay, you will either get a smaller output dimension, which is the case if you use valid, or you can get back the same output dimensions if you use same padding. Okay, I mean, you might be wondering why even bother having the same padding, right? Yeah, so yeah, anyone want to make a guess, like why people want to use like same padding in the network? Okay, let me give you a hint. Okay, let me give you a hint. So imagine you have an image of 8 by 8 dimension. Okay, and then we pass through a conv layer, which is basically the filter operation. So what is my output image after that? What's the size? And then if I were to pass through many conv layers, what will happen to the size in the end? So yeah, anyone want to make a guess? Like why do people have this thing called the same padding? Like and why do you think the use of the same padding is? I'll just continue drawing this diagram. Yeah. So yeah, maybe then we have the output here. Can you see my drawings, by the way? Yep. Okay, so maybe we just like ask like why do you think there's a need for same padding if we have very deep networks?
To avoid losing the data?
Yep. Thank you. Yeah, that's exactly right. So let's say if we have a conv layer that, let's say we have a conv layer that basically does a 3x3 filter with strike 1. Okay, what we expect is we will expect this to be like 6x6. Of course, in the actual conv 2D layer, there's another dimension here called the channels, which I will introduce you shortly. Okay, don't worry, this one, we will cover this later. Okay, so actually there's another thing called channels. Okay, but what you can see is that the output layer, the filter, if you use like valid, it will get smaller and smaller and smaller. And then like eventually you will get like very, very, very small output dimension, which is great if you would like to compress your data. Okay, but sometimes if you were to keep doing this, okay, you might compress it to a point where a lot of information is missing or lost. So if you use like the same padding, at least the chance of it like being compressed to a point where it loses all its data will be sort of mitigated, or like there's less chance that you will lose all your data halfway. Okay, so this is the idea behind this conv padding. Okay, so all good. All right, let me just clear this. Okay, so now, all right, now it's time to, yes, do you say something? Hello? Yeah, okay, so now is the time to go into the multi-channel convolution. So just now what you have seen is just having one. Okay, so if you look at the previous few slides, what you see over here is actually the operations for just like one slice of 2D plane. Okay, so in reality, in this convolutional neural networks, other than just having like one slice for the input, we typically have many slices. You can think of maybe like, you know, your 9-layer cake, or in Chinese they call it the 九层糕, right? So or basically anything like crepes, you know, multiple stacks of flat pieces. So in reality, a CNN is more akin to that, multiple stacks of flat pieces than just one single flat slice. So we call these different flat pieces the channels. So let us go through the multi-channel convolution. Okay, so the input, rather than just only having this 2x2, which is what we've been seeing for the last few slides, we actually have many copies of this 2x2. But of course, the many copies of the 2x2, they are all of the same size. So you can see the initial part here, this is of size 5, right? Dimension 5 for the height, dimension 5 for the width. Okay, we actually also have another dimension, okay? The third dimension, okay? So enter the 3D realm. Okay, in the third dimension, okay, so this is the height, and this is the width. And then over here, it is called the channel. Okay, why they call it the channel? Okay, it's actually, I think it's from some historical background, where in computing for colors, you normally have 3 channels, right? Red, green, and blue channel, right? In order to get your different colors, RGB, right? 255 pixels. So the initial image for a colored image is usually 3-channel image, like red, green, and blue. Okay, so that's probably where the channels came from. Okay, but of course, in the later layers of your neural network, as you go deeper and deeper, you are not restricted to just 3 channels. You can have any number of channels. Okay, I will share with you how you can get that. Okay, so imagine now you want to do a convolution on this multiple layer cake, where basically multiple channels. How do you do it? Okay, so as usual, computer engineers, right, they come up with a very ingenious method to do it. So what we just basically repeat what we do for one single slice, one single channel to the rest of the channels. So imagine this is your filter here. Okay, and this is your output kernel. I mean, this is your kernel for the, or this is your filter for the first level. So you will multiply like 1 times 0 plus 0 times 1 plus 1 times 0 plus, okay, so basically it's 1 by 1 multiply. So we just take all the non-zero and see. 1 times 0 is 0. 2 times 3 gives you 6. And then 1 times 1 gives you 1. That's why if you add up, like if you do a normal convolution operation, you get the output as 7. Okay, so that is for one slice. Okay, of course we are not, because different slices might have different kind of statistics. Okay, so we are not constrained to using the same filter or kernel on the same slice. So for the first slice, we use this kernel. Okay, on the second slice, we are free to choose another kernel to use. So you can think of it as choosing different features from the different slices. Okay, you don't have to choose the same features for each slice. So for the second slice, we can repeat the same argument. Okay, I'm not going to show the calculation here, but it's the same, like 1 times 2 plus 1 times 0, which is 0, plus 3 times 1, so that's 5. So you can see we apply the same convolutional steps to calculate this. For the last layer, we can also do 1 times 2 plus 1 times 3 plus 2 times 1, which will give us 7. Okay, so we have 3 separate filters or kernels for the 3 different layers. And then what do we do in the end? Okay, because in the end, we normally end up with only one like output layer. Okay, so in the end, the output layer, how do you do it? We typically have this 19 here. Okay, immediately, can you all see how this 19 is derived? Anyone can tell me how this 19 is derived based on the intermediate inputs? If I were to ask you like a question, how does this 757 give you 19? Can you all guess how does it work? Yeah, anyone, you can just do a guess. Yeah, I think the answer is here. Yep. Okay. So anyway, I'm just going to say the answer. The answer is you sum up the calculations from each of the channel into your overall output channel. Okay, so that's how we do it for multiple channel convolution. So 7 plus 5 plus 7 gives you 19. And that's how we do multiple channel convolution. Okay, so you might ask me, okay, you said earlier that you can have multiple channel numbers for the intermediate layers, but I only see you doing the operation here and only get one output. How do I get the second output, right? You might ask that. So the answer is very simple. The answer is that you can actually repeat this whole process with different filters. Oops. You can repeat this whole process with different filters. Okay, so you change this filter, change this filter, change this filter. You can get different output values. Okay, and then we can then sum the different output values to another filter here. So basically, you can have a different like layer cake here also. Like this is your first layer, and then if you just use kernels of different weights, you can have your second layer here also. Yeah, so that's the idea. So you can treat these different channels as choosing the different filters for your inputs. Like the first channel might find all the pluses over here. This one might find the plus. This one might be the plus filter to find all the pluses in your image. Okay, and your second one might be like a straight line finder. So it finds all the straight lines in your image. So yeah, different. If you use different kernels or filters, you get different kind of output activations over here. So that's the rough gist. Okay, that's quite complex. I pause here for a while. Any questions on this multi-channel convolution? Okay, all clear, because this is the most important slide right now for CNNs. If you understand this, you understand most of CNNs already. Okay, I'll move on. If you have any questions, feel free to just interrupt me, okay? Okay, so this is how it looks like in the big picture. Okay, so imagine my layer cake that I said earlier. I start out with a RGB layer cake, right? I like to say layer cake. Actually, it's like channels. Okay, so yeah, RGB channels. Okay, each of them having some filters. So over here, what I do is I will have basically a set of 3 filters that you can see here. 3 filters. Why 3 filters? Anyone can tell me why 3 filters? Okay. I mean, the answer is because there's 3 input channels, right? So I need to have 3 different filters or 3 different kernels for each of the slices here. So this slice will lead to this image here. Okay, then I have another second one, which will lead to the output of this second layer output. And then I have another one here, the third one here, which will lead to this third filter output. I have a fourth one. Where's my fourth one? My fourth one is here. Fourth one, which leads to this filter here. And then lastly, I have the fifth one. Let's use a different color, yellow, which will lead to this output channel here. So can you see that the output has a total of 5 channels? Can you see that? And each of these 5 channels uses 3 filters to apply on the original image in order to get my output. So you can treat this as like different features. This can be a straight line, this can be a horizontal line, this can be a curve finder, this can be a triangle finder, and this can be a square finder, something like that. Yeah. So you can use these filters to find stuff in the RGB image. And surprisingly, you don't even need to find the same features for the red, the green, and the blue layer. They can find different features, which is amazing, right? I mean, you would expect it to find roughly the same features, but you know, somehow this works. I don't know whether people try to constrain the kernels to be the same and then whether it works or not. That's interesting, because I've honestly never heard of people constraining the kernels. But yeah, you can find different features in your red, your green, your blue channels, and then you come out with different feature planes. They call this feature planes, which is basically the intermediate layers. Okay, so this is how we do it. And then later on, I will introduce you the last layer, which I didn't cover yet. It's called the pooling layer, which basically compresses the information into a smaller dimension. Okay, so firstly, okay, let's do some math equations here. Okay, so I hope you all like math. Okay, because now what we're going to tell is how many parameters are there. So this can be like a primary school math question. Okay, given the input has 3 channels, output has 5 channels, each of the kernel has dimensions M1 and M2, which means the weights. Okay, how many weights are there in total? How many weights are there for this? Okay, so yeah, I mean, I'm not going to give ask you for the answer because the answer is right here. Okay, so I'm just going to tell you the reasoning behind it. So how many weights are there? We basically take the channel input because there's 3 times 5. Okay, which is here, channel in, channel out. Okay, that will give me the number of this kind of gray squares here. Okay, each of these gray square, how many parameters does it have? It has kernel height and kernel width parameters in terms of the weights. Okay, then that will be the number of weights. Okay, now the question I'm going to ask you is, how many biases do you think there are in these few layers? Okay, so let me just give you some background for biases. So the weights are the dimension of the filter. The bias, each of these filters has a bias. So there's a bias for one of this. There's a bias for this one. So each of these gray color slices here has one bias applied to it. So anyone can tell me how many biases will there be in this convolution layer? So this is for weights. This is for weights. So assuming one of this black color thing has one of these gray color planes contains one bias exactly, how many biases will there be for this conv layer?
The chat says 15.
15. Okay, thank you. Yeah, that's correct. So that's 15 because we have 15 of this, right? You can see visually. Or actually what you can see is that actually the number of biases is just basically the channel in times channel out. So keep that in mind. Later we will see this in practice when we use TensorFlow. Hey, congratulations. I think you have mastered CNNs already. If you understand this, you understand university level CNNs already. Okay, I just made it in a not so math manner, but typically this is what you need to know. Okay, so let me clear this. Okay, so now I move on to this layer called the max pooling layer. Okay, there are variations of this. There's max pooling, average pooling. Some people have tried min pooling, but the idea is max pooling. In this square that you see, this purple thing, it just takes the max element, okay, and then outputs the result here. So over here we use a stride of 2 by 2. As you can see, we shift the filter by 2 each time we shift it. So what this helps with, okay, it makes the feature plane smaller. Okay, how does it do this? It's pretty obvious actually. You see, this is a 4 by 4, and then what I do is every set of 2 by 2 squares. Normally people do 2 by 2 for max pooling because if you pull too much, you lose more information. So in this 2 here, what I do is I map a set of 2 by 2 into a set of 1. Can you see that? Like 7, 3, 8, 7 that we see over here. The largest element is 8, and only 8 gets passed over here. Yeah. So this actually has a very useful property in that it actually helps with generalization. Okay, because there are many cases where you can have this set of 4 numbers. Okay, that will lead to the same output space of 8. So like, for example, an input like that will lead to 8. An input like that, like maybe like 8 at the top, 8337. An input like that, okay, guess what? It will also lead to the output 8. Okay, so this means that in the pixel space, you can permute your pixels a little bit here and there, and then the network will still recognize it in the same way. Okay, so max pooling actually helps with generalization, because by making it in a more crude form, you actually are able to apply the same knowledge you learn in various contexts to a new context that has the same kind of features, basically like the same kind of max pooling output. So you can see that this is like a many-to-one function in some sense.
Can I ask a question?
Yep.
So let's say you have an image with high resolution as opposed to an image with low resolution, but it's the same image. Do you want to alter this max pooling parameters to get, if you alter it to this layer to get the same result? For the same image, but one is higher quality, means pixel is smaller.
So you're talking about inputs with different dimensions, right?
Yes, but actually it's the same image.
Okay, it depends on the use case. Like if it's like classification, typically we want to, like, at the beginning of the network, we will try to make the pixels the same size. Like if it's like 16 by 16, we will downsample the higher resolution image to a 16 by 16 to feed the network. Yeah, so you don't have to change the max pooling layers inside. What normally people do is you change the input, rescale if needed, or upsample or downsample the image. Basically do your pre-processing step to make the input have the same resolution or same dimensions.
Okay.
Yeah, but definitely for high resolution image, you should max pool more. Okay, because you don't want to have the different little pixels affect the output too much. Okay, like for humans, normally when we see a scene, we only see the broad patches of it, right? You don't actually analyze, oh, there's a little speck of dust on your wall. You normally just see the wall. So for the max pooling layer, how I view it is something like also making the input more blur so that you don't over focus on some non-essential thing. You see the broad picture in some sense. I mean, max pooling is sort of like blurring the image, right? If you think of like combining every 4 pixels in your image to just 1 pixel, it is essentially blurring your image from a high resolution to a low resolution. I mean, people might think it's stupid. I mean, why lose information like this, right? But it turns out that losing information like this actually can be helpful to generalize, to learn classifications of like dogs and cats. You may not want to know the specific features of the whisker. You just need to know that there's something coming out from the face, and you know that's a whisker. I hope that helps with the understanding for this.
Yep, thanks.
Okay, so max pooling is a very important layer that people normally use for convnets. Of course, there are people who also say that, you know, you can reduce the size. Okay, so this can be a trivial question. So imagine if I don't want to use max pooling, but I want to reduce the dimensions of my output. Based on the techniques that we learned earlier, how can you reduce the size of your output without using max pooling? So you think I've covered quite a few techniques that could be done with the convolutional networks. So if our aim is to reduce the dimension of our output size, what other techniques can we use to reduce it? Anyone? So I'll give you a hint, it's about shifting the filter. There's a parameter to decide how much to shift the filter by. You all remember what it is? It starts with S. I think the answer is on this slide also. Okay, so
Strides.
yeah, correct, strides. That's right. So if we increase the strides for our filter, we can actually look at a larger image and then we skip a lot more details, and hence we will have a lower output dimension. Thank you. Thanks for the answer. All right. So that's exactly what people do for ResNets. ResNet is called residual networks. They use a larger stride in order to downsample the output size. Okay, but whether is it the right approach? I personally don't think so. I think max pooling is still more efficient because you actually have some semantic meaning behind max pooling this. You are blurring the image. If you take the strides like that, you might actually miss out some features. So actually, there's no right or wrong answer. Some people use max pooling, some people use strikes. So can try both. I mean, most if you use the pre-established architectures like ResNets, you'll be using strikes. Okay, they don't really have max pooling in ResNets. Okay, but if you use architectures like the VGG, okay, actually these two architectures I didn't put them in my slides, but I recommend you to search them up. So they are very deep networks. VGG commonly associated with VGG 19 for 19 layers, and ResNet. ResNet, there's many different layers as well. So ResNet, the most popular ResNet is called ResNet 50, and as you can imagine, ResNet 50 has 50 layers. Yeah. So if you're interested, I can cover them in another session. But all these very popular nets, and also there's Inception Net. Yeah. Inception ResNet. So all these are very popular CNN networks that people use. Okay. There are actually a lot more to name. But I don't need you to know like all this. Okay, you just need to know maybe ResNets, because I think ResNets is still the most popular and the most I think one of the more efficient networks. Okay.
For these nets that are pre-trained already, can you do transfer learning on them, or do you have to take whatever input output they give you?
That's a good question. So for transfer learning, it matters a lot whether the earlier features actually match with whatever domain you want. So let me just draw a diagram. So if let's say I have this pre-trained network, so my pre-trained network, I have a certain features here, feature space over here, feature. I'll just write feats. Okay, maybe I can write feature. Okay, so we have a feature space at the end here, which is like the almost last dimension. Then normally, if let's say you want to do your classification, you will put a fully connected layer here, right? Right. Then we have the output. So if let's say our feature space here, okay, is very similar to like what your output is. So imagine if let's say your feature space here is trained on ImageNet, and then you want to do like a cats versus dogs classifier. What you can do is you can then delete the last layer that people use for ImageNet, okay, and then you can just so for transfer learning, you don't use this last layer, you train your own fully connected layer here, and then you have output classifier for cats versus dogs. So over here you have only two nodes. One is for cats and one is for dogs. Okay, the initial one here is like 1,000 different outputs because ImageNet has 1,000 classes. So what we do is, if you want to do transfer learning, okay, we delete away this last layer, and then instead we train our network through this layer instead. Okay, so the case where transfer learning can help is when your output features here, you expect them to be very similar to your to whatever you are doing. So ImageNet has a lot of animals. So cats versus dogs using ImageNet pre-training, I think is very helpful. In fact, you may not even need to do any training at all. You might just be able to, okay, you still need to do some training because of course you need to give it the example of cat and dogs. But for this feature layer here, you can actually just freeze this layer. You don't even need to train this layer because I'm very sure ImageNet has cats and dogs. What you're doing is just taking a subset of the classes. But then if let's say you are training a classifier to classify maybe stationary objects like pencil, pen, ruler, then ImageNet, it may not really help because the features that it generates, there are many animals, maybe some people, stuff. I mean, I'm sure it will help a bit because at least it learns how to associate like animate objects, inanimate, rather the shape of the object should be captured somewhere up here. Okay, but I mean, for those like that, transfer learning can actually not be very effective.
Is there some sort of description on each pre-trained model? Like, oh, this model was pre-trained mainly on so and so images, so
yeah, of
better
course.
for
So when you go to, so if you want to take these pre-trained images, you can actually use like TensorFlow Hub. They actually have a lot of the stuff, and most of them are trained on ImageNet. Yeah, so if your domain happens to coincide with whatever training set the ImageNet has, then you're quite lucky. Yeah, if not, actually, like if you want to do other stuff, like you want to do a food classifier, maybe cucumber, carrot, or this, maybe you have to provide your own training samples. But you can still use the features from ImageNet. I mean, it won't hurt because there's some initial features already extracted that might help out.
Okay.
Yeah.
Okay.
So yeah, you can actually search like TensorFlow Hub. I'm pretty sure PyTorch has their own hub as well. but I've used TensorFlow Hub. I find it very easy to use. I think the future of deep learning will be mainly transfer learning, actually. People spend months to train a big model. You just sort of take the progress that they have and use minimal effort to just adapt to your own domain. So that should be more or less how deep learning should be done in the future. It's already being done like that now. Okay, but of course, we are going through all this today because it's nice to know how things work so that you can change the model to your needs accordingly. Okay. Yeah, thanks for the question. Anyone else has anything to add? Okay. If not, I'll move on. So let me just share with you some strategies of going to the feature layer, which is like the conv layers, the layer cake, into like maybe a last fully connected layer. So of course, this is for classification problems. If you want to do stuff like segmentation, then your last layer will be like pixel space, which is like each pixel, which class it belongs to. So over here, the output, okay, is typically this for classification. Of course, you can also use a similar model for like pixel segmentation, that kind of thing. Yeah, object detection. Object detection will have additional features like bounding box coordinates and stuff like that. Yeah, but now this case, I'm just talking about a very simple case of classification. So for classification, typically there's two strategies that are being pursued. Okay, one strategy is where you just do a flatten. Basically, you take all this red color stuff, like for example, if this is a 4x4 layer, if we flatten it, what will happen is that we will make this entire thing become a linear layer of 16. Yeah, and then you can basically like do that for every single channel of your last feature layer. You can get a fully connected layer like this using a flatten. Then we will have a output here with the fully connected layer. So this number of nodes here corresponds to the number of classes that you have. So like over here, there's 4 classes. Yeah, so this is the fully connected approach. And yeah, this is what people normally use, okay, for the classification problems. And it's quite effective actually. Okay, so this is fully connected. Okay, there's also another strategy called global average pooling. Basically, you come up with the number of feature maps in your last layer according to the number of classes you have, like 4 classes in this case. Then you just take a global average, which means the average of this red layer, and then this will be your output to the classification node. Yeah, so this is called global average pooling, which its name implies is that you globally, in the channel itself, you average the contents or output of your channels. Okay, and this output will basically be a node here that you use for classification later. So as you know that once you use classification, you have to apply another layer. Okay, so this is a great time to do a revision. So let's say I get the output like 15, okay, 10. Okay, the output here doesn't really matter. I'm just showing you that what kind of numbers you expect here. Like after you do an average of all the activations, you get these numbers here. But remember, when we do classification, we want probabilities at the end, right? So can anyone tell me, when we have numbers like this, these are called logits. If we want to get to probabilities, what must we apply to this to get the probabilities? So this will be a good revision for the MLP part. So yeah, what's the thing that we can apply to like this logics here to get probabilities? I mean, the same thing happens for here as well. Yeah. Anyone? Yeah. So there's a kind of method to convert some initial numbers to probabilities. Okay, so the method actually, okay, I mean, I see everyone's quite quiet. Okay, so the method is actually called the Softmax method. Okay, so I'm going to revise this thing if you forgot what it is. It just converts the logics to a output probability distribution. And so this basically is what is done from feature space to output space for classification problems. Okay, moving on. Okay, so one of you asked about dropout, I think 1 or 2 weeks ago. Okay, so I've decided to cover it. Okay, so dropout is typically applied, okay, in the fully connected layer. So we go back to the graph here. So people have found out that actually, if we just do a fully connected layer here to the output layer, like that directly, actually, because the MLP, remember, yes, no, is fully connected. the relation you learn can be quite messy. Sometimes you can have a certain node being very dominant and then the rest not very dominant. So there are some problems of like maybe generalizability. And so people normally apply a dropout layer here, right at the end here towards the classification in order to help the network learn better. So that was the reason for dropout. So dropout is a very interesting idea. Okay, so dropout, what you do is that during training time, okay, you don't want the network to like overfit to a certain, let's say you have a very strong node here, then this node takes all the gradients here because the rest of the nodes are very small in terms of the output activation. So if you have one very dominant node here, what will happen is that only this thing learns, then the rest doesn't learn very well. And that can be the case when there's many nodes. So in order to, so this is actually a problem with fully connected networks actually, or MLPs, multi-layer perceptron. If you use something like that, you might have a very dominant node. And then basically, if this node learns the things wrongly, you are sort of like, you don't have a backup. So in order to have a gradient flow through more than one path, okay, you actually can employ this technique called dropout, where you just, during training time, you just take a certain probability, you randomly drop out those nodes. So like all these X here are those nodes that are dropped out. Then you do a forward pass of the network without those nodes. Okay, so you can see that this is the dropout methodology. And you can see that, you see over here, this is a mess. This is a forest. Over here, we only have a few trees. We have chopped down a lot of the forest trees. And so the connections are also reduced. So what this forces the network to do is that each node will actually have to learn some meaning, because there can be a case during the training that the node that is dominant here is dropped out. Okay, so if it's dropped out, other nodes need to pick up the slack. They need to learn the relations as well. So, I mean, the paper by Dropout says that it's something like doing many different ensemble methods, like, you know, random forest, you do different ensembling and then you average it. So this is in theory, or rather this is intuition, but not proven, okay? But overall, Dropout helps to let more nodes learn. Yeah, so I guess there's some benefits to this. So the issue is if you drop out those nodes during training like this, you will actually have a lower activation value here. Because why? It's actually quite intuitive as well. You have fewer nodes contributing to your value here. Your value will tend to be lower. Okay, especially if you use like ReLU activation. ReLU activation, the output is always positive. So if you have fewer nodes connecting to it, you will always like have fewer lower activation value here. And what this happens is that your output here will not be the true output. So what people do, okay, is we do some scaling. So normally dropout in practice is done with a scaling during training time. So let me go through the text here. You keep a proportion P of nodes, okay? And then basically the other 1 minus P, like maybe P here can be like 40%. You keep 40% of the nodes. So P will be 0.4. Then 1 minus P will be 0.6. So if we do an expected value, okay, of the nodes outputs, we will get the nodes, maybe it's like Px. Okay, so in order to get the overall activation value X, okay, what we will do is we'll do a very simple scaling. We just divide by P, and then we can get back the overall value X. So this means that if we drop out a certain proportion P, keep a certain proportion P of nodes, we just need to apply 1 over P. So you just multiply the activation value by 1 over P in order to get back the same kind of magnitude as though you didn't drop out any node. Okay, so these are some tricks to make the output value become the same. So during test time, you do not need to drop anything at all. You just keep the fully, you just need to keep the fully connected network like this during test time. Okay, so that was a rather lengthy description that I had there. The main takeaway from this slide is that dropout helps to prevent a node from learning all the good stuff, but instead spreads out the learning across multiple nodes. Okay, that's the main takeaway. Okay, and also this proportion P, you can toggle it using TensorFlow. I will demonstrate later how to do it. Okay, questions for this? All right, let's move on. So there's also a way to like visualize filter weights during when you do the Comp2D, but usually you can only like reliably visualize maybe the first filter weights. Okay, because the subsequent filters, if let's say you have more than one channel, you actually have a combination of the earlier few channels to form your overall filter weights. So like over here, you can see this one, I did the filter weights using a method to just like, it's basically a SNS Seaborn heat plot. Okay, if you all know heat map, sorry, Seaborn heat map. Okay, so this was done using like a simple Conv2D. It's in the notebook actually. So what you can see here is you can see like the darker squares are the higher magnitudes and the lighter ones are the smaller magnitudes. So you can see that each filter is actually learning different things. Like maybe this one can be like an L shape at the top. This one can be doing like trying to find like a blank at the middle and so on. So each filter, this one is like maybe a vertical line at the center. Each filter is learning a different kind of aspect to capture, like an edge, a diagonal, and that kind of thing. So yep, this is how CNN filter eventually becomes after we do some training. So overall, if you were to like, for example, take the mean of the filter values and add them up together, like what they did in this deep belief paper, you can actually see that the filters, okay, if you train it long enough, you will see like, well, layer 1 is more like edges, layer 2 maybe is more like, if this is a face classifier, it's more like different parts of the face, and then layer 3 is like the different kinds of faces. So yeah, this is what a neural network typically would do if it's trained well. So the more layers you go through, the more higher level features you obtain. Okay, so this is like a CNN explainer here, which I thought was quite cool. So I'm just gonna show you like a little bit. Okay, hold on. Let me just share this with you. Okay, so if you click on the link in the slide, you have the link by the way.
The slides are uploaded, but
let me just copy and paste the link there.
Better, yeah, it's better if you copy and paste.
So you can go to the link here. Okay, and then what you will see is that there's this CNN explainer here that basically tells you like the different layers in the CNN. And over here we have a cup. So the output here, okay, I didn't create this by the way, but I thought it was quite cool to visualize what is happening. So the output here is like the different classes for the classification. So input here, we have 3 input channels, the red channel, the green channel, and the blue channel. So what we'll do here is like at the start, okay, we do like, if you click here, you can see what's happening. We will add the different filters here. The filters will go through the different, basically, it will go through the different parts of the image, and then it will sum up to give you this intermediate conv layer here. And as you saw from the earlier slide, if you have 3 channels, you sum up 3 times. Okay, and then you have a bias, and then you put over here. Okay, so this is how we do it. Okay, so over here, there are bias. If I remember correctly, the bias actually for each of these filters. Over here, the bias seems to be a global one. Okay, doesn't matter. Later, we'll verify this. Okay, so this is how the conv layers does it for the intermediate one. I mean, I think this visualization is quite cool. You can see this is like the intermediate. This is the intermediate layer activation values, which looks pretty much still like a cup right now. Then we pass it through the ReLU. Okay, ReLU, basically you can see what happens is the ReLU activation just takes in the maximum value as the output. So you can see that those regions that are like negative in value, okay, will be removed and then will be replaced by 0. So this is the ReLU. Then we do a max pool. So max pool layer, as I explained earlier, is taking like a larger size of the pixels and then compressing it to like maybe one size. So like here, you can see that it's a little small. Okay, I zoom in. Can you see my zoom by the way? Yeah, so I zoom in. So over here, you can see that this is like a 2x2 here. And then the output is just 1x1. So it actually just takes the maximum pixel and then comes with the output. So this is the max pooling layer. After that, we go through the intermediate layer again. You can see over here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 different channels in the intermediate layer. And then we will go to this output layer here. Okay. And can anyone tell me how many channels are there in this layer? So the input, we take in 10 channels. The output here, we have 28, 28, 10. So how many channels are there in this output? conv21? Anyone? So the answer is one of these numbers here, of course. So yeah, I just pause here for a while. to just see whether you understand. So how many channels are there in this conv21 layer? Yeah, you can type in the chat also if you don't want to say it. Yeah, 10 layers. Very good. So this is 10 layers to 10 layers. Okay, very good. Then we do the same thing for conv22. So another 10 layers. Yeah, you can see that here is 28 pixels, here is 26 pixels. So they didn't use they didn't use the same padding. They used the valid padding instead. Okay, that's why there's a decrease over here. Okay, then when we do a max pool, you can see that from 26 we reduce to 13 13. Okay, why? Because I mean the same thing again. You take 4 pixels like that, 2 by 2, and you reduce to 1 by 1. And finally, at the end, when you want to like do this fully connected layer, what they do first is they flatten the. So you can see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 different channels. Then each channel has 13 by 13. Okay, and then 13 by 13 gives you 169. So you have 169 nodes here for each channel, and there are 10 channels. So how many nodes are there? 169 times 10. So this one is like channel 2, channel 3, channel 4, channel 5, channel 6, 7, 8, 9, and this is lastly channel 10 nodes. So we flatten the entire thing into one long node, and then we can actually do like a softmax after that. Okay, so yeah, the softmax is just this exponential thing here. So actually, I quite like this thing. This is quite cool, the visualization. Okay, and then after that, you can see that they convert into logits, and the logits to probabilities, and the highest probability is called the espresso. Yeah, so this is a broad eye view of how the CNN works. Okay, I don't have much time to look at the other pictures, but I encourage you to take a look at this site, okay, because it's quite interactive. It can let you see like behind the scenes of how the neural network works for CNNs. Okay, I'm gonna stop my share here and go back to the slides. Okay, where's my slides? Yeah, this is the slides. So yeah, go play around with it. Okay, I don't have time to go through more with you, but do play it out by yourself and see whether you can like get some insights and learn this better. The dimensions are all at the top here, so it's very, very helpful for this. If whoever did this, I think it's a great job. Yeah. So now we talk more about how to code this in TensorFlow. I think this will be of interest to most people, how to code it. So recap, what is a fashion MNIST data set we are using? It's a data set that contains 10 classes of different clothing items like t-shirt, trouser, pullover, dress, and so on. These are the classes. Each of them is a 28 by 28 pixel. Grayscale. Okay, so now is a great time to ask this question. So grayscale, how many channels are there in the image? So you know RGB color channel is 3 channels. If the image is grayscale, how many channels are we expecting? Yeah, so I'll just open up to the floor to see whether anyone want to just guess. So if it's grayscale, that only has like between white to black, how many channels do you think the image has? 1. All right, thanks, Teji. Yep, that's correct. So you only have the black and white channel, which is like 1. Yeah, it's either black or white, and in between. Yeah, so the channel is 1. Okay, so do take note, if you are doing color images, your channel will be by default 3 because you have RGB, red, green, and blue. Okay, so this is how we define the TensorFlow model. Okay, so I'm just going to go through roughly what are the filter layers. So we have the input layer again, which tells us the input 28, 28, 1. Okay. Then I have a new layer that we have. First time we see this layer is called conv2d. Conv2d takes in the number of filters, which is like the number of kernels that we. Okay, so this filter is actually, you know, when you do your layer cake output, is the number of layers you want for your output. So a filter size, a filter of 16. Okay, it means that we will have output channel size of 16 at the end. Okay, then we have a kernel size. Kernel size is basically the your filter size, like, so it's a 3 by 3 weight matrix that you multiply to different parts of the image. So that's kernel size of 3, 3. Also can be written as kernel size equals to, also can be written as kernel size equals to 3. Okay, if you just write one of them, they will just interpret that you mean 3 for both dimensions. Same thing for stripe, you can also just write stripe equals to 1. Okay, padding, remember this part here, padding, that's same and valid. So I hope you remembered, same padding means that your filters, your your filter dimension will remain the same. So what this means is that initially my shape is 28, 28. After I apply same padding, after I apply same padding, I expect the output size, okay? So the output for this layer should be 28 by 28 or so, because I use the same padding, means the input dimensions are preserved. Okay, so how many channels are there at the end? So initially there's only one channel, right? But here I have 16 filters. So the output dimension is 28, 28, 16 for 16 channels. Yeah, after that, I do max pooling 2D. Max pooling 2D, remember, it takes a 2 by 2. Okay, over here, the pool size you can determine. You can do 3 by 3 also. Okay, of course, you can also do pool size equals to 2 over here, and they will automatically infer that what you actually mean is that you mean 2 on each dimension. Yep. Oh, I'm annotating wrongly. Okay, I just wanted to. Okay, so this is what it means. After that, when we do this code block, okay, later we see the dimensions, but let me just explain over here. This one will get 28, 28. Oh no, wrong. This one will get 14, 14, 16 because we do a max pooling. Okay, then after that, we do a flatten layer. Flatten, as you remember from the visualization, it means that from filter, you just expand out all of this into a linear layer. Okay, it's basically 14 times 14 times 16, the number of nodes. Then we do a multi-layer perceptron with 1 to 8. And then finally, we do 10 softmax. Okay, so actually, if I have time, I would like to ask, like, why is that 10? Okay, but I'm just going to give you the answer now. It's 10 because it's the number of classes for fashion MNIST. There's 10 classes. So for classification, your final dense layer or final fully connected layer should contain the number of nodes for the number of classes that you have. Okay, so again, we can visualize the model in this flowchart. Input, comp2D, max pooling, flatten, dense, dense. It is a very simplified model with just one comp2D and one max pooling. Okay, so this is how it looks like in the end. So what happens like this is what you have here. Okay, you have one channel, 16 output channels, and filter size 3 by 3. So remember the formula, 1 times 16 times 3 times 3 is the number of weights. Okay, so I realized I've said something wrongly just now. Okay, remember I said that the biases are for each gray slice. Actually, it turns out that all three kernels, all three filters that you use for your input, all uses the same bias. So yeah, so correction on that. So like the earlier number of biases should be only 5. Okay, based on the number of output layers we have, each output layer has only one bias. Okay, so it turns out that there's 16 biases. Okay, so I made a mistake earlier. Okay, so do take note. So if you add those two up, 14 plus 16 will give you 160 parameters. So that's 144 weights and 16 biases. All right. So for the next one, dense 2. Okay, then after you see the flattened layer, 14 times 14 by times 16 should give you this number actually. So the number of parameters that we should have here is, if you remember correctly, it's the input nodes times output nodes, 3136 times 128. Okay, and then the biases will be for the number of output nodes. Actually, the structure you can see is very similar to like the filter. So the output, you see there's 16 channels, so you have 16 biases. Here you have 128 nodes, so you have 128 biases. We can apply the same formula for this. 128 times 10 weights plus 10 biases is 1290 parameters. Okay, so this is the number of weights we expect from the diagram. Okay, so I have a question over here. This one maybe you all can answer. The max pooling 2D layer here has no parameters at all. Why do you think that's the case? Right, so the question will require you to understand, like, for the max pooling 2D layer, is there a need to have any learned weights at all? Or is the operation like fixed? You always do the same thing regardless of like your input. Okay, I mean, if there's no answer, I'm just going to continue. But I give some chance, okay? I give maybe about 10 seconds for anyone to just say, why do you think there's no weights needed? for this operation of max pooling, like 2 by 2 to a 1. Okay. Chicken, you were about to say something, is it?
No, no. Carry on, please.
Yeah, so there's no weights required because if you want to do this max operation, it's just simply doing the max parameter. You don't have to have a learned weight to do it. It's what I will call a fixed algorithm. So it is a fixed algorithm that you use. You don't have to learn how to do it. It's inbuilt in the model to do max. So that's why max pooling 2D has no parameters needed. Okay, while all your filters, you actually need to learn the filter weights because you need to learn how to interpret different images. Okay, that was a handful. Okay, I hope this was clear. Okay, so this is how the code should look like overall. Okay, so we have a data set, take in the train and test samples from the load data function in Keras. Okay, we scale by 255. If you remember correctly, this scaling just means we reduce the dimensions to between 0 and reduce the range of inputs to be between 0 and 1. Okay, because the pixel values are between 0 and 255. Then this is our model that we saw earlier, how to do a single conv layer with a single max pooling layer, and then flatten, dense, and output. Okay, optimizer is the same as before, Adam sparse category cross entropy, because we are using softmax probabilities. Okay, and then in the end, we also put in an accuracy parameter to see how good we are at predicting the images. We feed the model, okay, and then we evaluate the model. Okay, so one thing that has changed over here as compared to the multi-layer perceptron code 2 weeks earlier is that I did a reshape over here. Okay, this is necessary. Okay, because for conv 2D, they expect a 3D vector. They expect a vector with 3 numbers here. The height and the width of the kernel plus the number of channels. So 28 times 28 times 1. So we need to reshape it to 28, 28, 1. Okay, because initially the shape was actually 28, 28 only. So we just added one more dimension there for the channel. Okay, pause here for a while for any questions. Okay, if not, I would like to spend maybe the last 5 to 10 minutes just going through key parts of the notebook, and I leave you to do the exploration questions on your own. Okay, so let us load the notebook. So I think the link is in the chat already. Let's go to the notebook. Let me just stop my share and run the notebook. Okay, can you see my notebook, by the way? Just give me a thumbs up if you can see this using TensorFlow for classification. Okay, so we'll go through the notebook step by step, and then we will like look at what is there. So actually, this notebook should be quite easy for you now because I think we have covered through the most important parts of a CNN, like the multi-channel and everything. So now you will just see how to implement this out in code. Okay, so let's go to the runtime. Change runtime type, choose GPU. Okay, if you choose a CPU, you will take quite long to run it, like I think 4 to 5 times longer. So GPU. So you see it's connecting. Let us just run this to run the cell to let it connect. So we are using the cloud GPU that Google provides. Okay, and over here you can see already. Okay, this is what we have. Actually, this is not the CNN. This is the MLP model. I just put this model here for comparison later to see like what are the accuracies we have here. So the MLP model, remember, we just have 28, 28. Okay, we just flatten it. Okay, and then we just pass it through a 1 to 8, 1 to 8 nodes and 10 nodes. So you can see later in the CNN, we will add more layers here. So what is the performance for this very rudimentary model of just using a multi-layer perceptron in order to classify the image? So let's run this. Okay. So you can see that it's about 87% accuracy around there. Okay, wow, this can go up to 88. Okay, so we got lucky here. Sometimes the initialization can actually affect the model a lot. So now we got 89%. Okay, but usually it's maybe about 87, 88. Oh, so this was the training. So the test is around 87%. So can we do better with a CNN? Okay, I mean, of course, the answer has to be yes, right? If not, why do we learn CNNs? So over here, this is the model that we saw just now in the PowerPoint slide, if you remember, exactly the same code. Okay, let us plot the model to see how it works. So you will see that this is the model. And then we can see the model summary, which is what we saw in the slides as well. Okay, the same thing. So we do a compile and a fit and evaluate. Okay, over here, I also reshaped the test images. Yeah. Okay, so let's see what this naive CNN model, which basically only has one Conv2D layer and one max pooling, what accuracy can this give us? So you can compare the params is like 402,986. This up here is about 100,000 params. Yeah, so it's about 4 times more params. MLP has 101770. So you can see that already just giving it only one Conv2D. And then what I do is I actually have only 16 filters, 16 channels, which is quite little for modern CNNs. You can see that it has achieved, after 5 epochs, it has achieved about 91% accuracy. I mean, I got 91 during my test run, but let's see how it works. Okay, so we need to wait a while it does its evaluation. So actually, this is more or less the only code I'm going to run for today. Okay, the rest of the code I will just touch on a little bit verbally, and then I invite you to just finish the rest of the notebook. Okay, actually, I did most of the notebook myself for this. So it's just exploring how CNNs can be modified. Okay, so 91.1, I got it. So now I got about 90.6%, but you can see it is much higher than this 87%. So what does this mean? It means that, of course, number one, the more parameters, maybe the better it fits. But the other thing is Conv2Ds are of the right structure, or convolutional neural networks are probably of the right structure to handle images because of the way that it goes from like zoom in the image and then you zoom out through the feature space, gradually building from the lower levels of features to the higher level, more complex features. So that's what we can get. Functional API, I leave you to explore on your own. This is how we do. Earlier was sequential up here. This was sequential. So this part is how we do in functional API, the exact same model. So we can visualize the predictions as well. So this code, I'm not going to go through, but this code basically just look at some random images and then just see whether or not the image is classified correctly. So if it's wrong, it's red color, correct is green. So you can see actually not too bad. It classifies most of it correctly. Only like stuff like this, it predicts a pullover. I think this should be a jacket, and this one should be, no, it's supposed to be a pullover, but it predicts as coats. Let me see here. Yeah, so it predicts a pullover, but it's supposed to be a coat, and this one it predicts a shirt, or it's supposed to be a coat. So actually, if you ask me, I think it is actually quite accurate because like this really looks like a shirt to me also. This looks like a pullover to me also. So in the image domains, you realize that actually a lot of the data sets, some of them might be mislabeled. Okay, so I mean, this shirt and this shirt looks the same, right? If you ask me. Yeah, so I wouldn't penalize the model for this actually. Same for this. This also looks like a pullover, right? I mean, this and this looks quite similar, right? This is a pullover. Yeah, so we can also classify, like you can run this more and then you see a random selection to just see like where it went wrong. Like this one, definitely I would penalize the model because this is a shirt prediction, but this is obviously a trouser. So yeah, I didn't really learn this. Pullover, but predicts coat. Sorry, predicts pullover, but it's supposed to be a coat. Okay, this one I can understand. Okay, because this one, I don't think this looks like a pullover. So yeah, these are some genuine cases where the model actually got it wrong. Okay, the rest, but actually the rest, see, it classified pretty well. So yeah, CNNs are pretty good. So we can also visualize the filters. Again, this is basically just looking through the layers. We just predict only the number of filters, like maybe in this case, in the first layer of filters, this is exactly what we like, something like what we showed in the slides earlier, like how they predict the different ages in this filter. Okay, so yeah, you can run these exercises and see what will happen. can we increase more Conv2D layers and improve our performance? The answer is yes. Okay, actually, no, not really, because using just one more extra Conv2D without changing anything else, okay, didn't really get the accuracy needed. Okay, we can add more filters. More filters means like we increase the number of filters in the first layer. And yeah, it got 91.7. So it may be that the number of filters in the first layer was not sufficient to capture all the information needed. So you can toggle these parameters as well. Next up, we do like double Conv2D layer with max pooling with increased filters. And you can see like the output is like 91.7, which means that maybe the additional conv layer didn't really help much, but it's mainly the number of filters that help. So I have no hard and fast rule as to what can help, what cannot help. Okay, it's more or less experimentation at this stage. Okay, now we add dropout in the final layer here. We add one more dropout. So this is how we add a dropout layer. Okay, and then what we get is like about 91.4, around the same. So dropout actually didn't really help much for this problem. So then I experiment. What if we use a larger filter size, like 5 by 5? Okay, here we change 5 by 5. And then actually it got like 91.2. It didn't really work out that well. But you can see 5 by 5, interestingly, you can capture like more complex shapes. You can capture like diagonal lines here. You can capture some lines here. Yeah, but for this use case of simple fashion MNIST, 5 by 5 didn't really help out much. So yeah, so normally people use 3 by 3 actually. It's more dynamic, more versatile, can capture more features that can allow greater stackability. Like if you do 5 by 5, it may not be that general, and then you have problems like stacking up in the next few layers. Okay, so if you have more layers, you don't need a very high filter number at the first layer. Okay, stride size 2. What if you use a larger stride size instead of just stride size 1? Okay, actually I got a worse result. So you increase your stride size, actually you are losing information in the model. So use sparingly when you do the increased strides. Okay, global average pooling. So I tried out to see whether global average pooling can work better for this use case. So remember global average pooling, we end up with like the 10 filters at the end, the number of classes. We do global average pooling. Okay, and then we do like the final 10 nodes here. What we get is like about 34.9, which means that maybe a global average pooling may not work out well in this case. Because usually global average pooling, they actually have a very dense, a very deep model, then they do global average pooling at the end. Okay, so yeah, it didn't work out that well. So yeah, I gave you an exercise here, how to get greater than 92% accuracy. Okay, of course, if we use more complicated models, we can get greater than 95%, 98%, but those require like ResNet 50 kind of models. Yeah, so 92%, I just basically did like, this is like BGG style. You do the filter twice, then do a max pool, do filter twice, then do a max pool. So just using that, I got like 92.6%. So, okay, this was a rather long session. I would like to end it here. Before I end, maybe I'll just ask like 1 to 2 minutes. Anyone has any questions? Okay, if not, yeah, thanks.